Okay guys, this is the colour of complexes, or just complexes really. So a complex is when a ligand donates a lone pair of electrons to a central metal ion to form a dative covalent bond, or a coordination bond that's sometimes called. And there's really only a few, there's only about 10 or 12 different complexes that you need to know the colours of. You also need to be able to figure out the charge of your complex by knowing the charge of your metal ion and the charges of your ligands. Now, you won't be told the charges of your metal ions or your ligands. If it's iron, they'll probably tell you whether it's iron 2 or iron 3, but they won't tell you about any others. So just remember, copper is 2+, and cobalt is 2+. Iron can be 2+ or 3+. Look for the Roman numerals after it. So if they had that would be iron 2+. This would be iron 3+, okay? So just remember that. You also need to remember all the different charges of all the different ligands you could come across. We have water, which has a charge of 0, ammonia, which is 0, thiocyanate, which is -1, cyanide, which is -1, chloride, which is -1, and hydroxide, which is -1. So they're almost all the ones you're going to come across, either 0 or -1. Okay, we call these neutral ligands, these top two. So take those down, try and remember them, especially these top two and the bottom two, because they come up an awful amount. So bearing all those charges in mind, I've popped up a few bits and bobs on the board, a few different complexes. I'm just going to add a few more. Okay. And all we're going to do is go through what the charges of each of these will be. Bear in mind those rules we've just said. So, I know copper has a charge of 2+, and I know water has no charge. So overall, this complex will have a charge of 2+. Again, copper is 2+, I know water and ammonia both have no charge, so that will be 2+. I know copper is 2+, I know each of my chlorides is 1-, so +2 -4, will give me a 2- charge. And here, hydroxide is 1-, copper is 2+, so they will completely balance out to give no charge. Here again, cobalt is 2+, water is nothing, so that'll be 2+, 2-, and again, that'll completely balance out. Over here, my iron is 2+, look, it says, we've got those Roman numerals, there's two little dashes. Water is nothing, so that'll be 2+, and my hydroxide will completely cancel. Again, this will be 3+, because now it's iron 3+ we're talking about, and my hydroxides will cancel. So we've now got our proper formulas with the charges attached. If you forget to put these charges there, you'll definitely lose a mark. It's really important you do that. So really, I'm just going to go through the colours. I mean, I guess you could learn this from a sheet, but I guess if I put it on a video, it might help it stick in a little bit more. So your hexa-aqua copper, 6 waters bonded to a copper, that is just a blue solution. And it's really important you follow each of these letters, each of these colours, by either the word solution or precipitate. Now I'm going to abbreviate, don't abbreviate in the exam, actually write the word solution or precipitate. This is a very interesting molecule actually. This has got lots and lots of stereoisomers, and I've got a whole video based on this molecule here, this complex. This is a deep blue solution. And I'll be talking about how we can make this into this after I finish this little bit. We have my copper chloride, which is a yellow solution. Sometimes when we're changing from hexa-aqua copper to copper chloride by adding hydrochloric acid, the colour you get is green. So people think that this is green. If you do get a green colour, it's because you haven't added enough hydrochloric acid, and only some of your hexa-aqua copper has changed into copper chloride. So what you've got is a mixture of your blue and yellow colours, which gives you a green colour. So if you do try this experiment yourself and somehow get your hands on some chemicals and it changes green, basically you've not used either concentrated or just enough acid in there. And we have my copper hydroxide, which is a blue precipitate. So that's a solid, that is. All of your hydroxides are precipitates. Here we have a pink solution for your cobalt, hexaqua cobalt, and that will change into a blue solution if you change the waters for chloride. The hydroxide, again, is a blue precipitate. For iron, we go for iron 2. The hexaqua iron 2 is a green solution, and that will change into a green precipitate if we substitute the waters for hydroxides. Here, your iron 3 hexaqua will be a yellow solution, and if we change the waters for hydroxides, it will give you a red, or a brown, I guess you could say, precipitate. So they're all your colours. They're all the ones you need to know if you do OCR. If you do another syllabus, there might be a couple of extras or a few less from there, but these are definitely all the ones you need to know for OCR. Okay? So what I'm going to talk about now is called a ligand substitution reaction. It's how we can change one complex into another. And we'll start with copper. So what I can do is I can start with my copper solution, and they'll probably call it a copper solution, but what that actually is hexaqua copper, because obviously your copper will bind to the waters. Your waters will donate that lone pair of electrons. And let's say we react that with sodium hydroxide or potassium hydroxide. Now, although you're adding, let's say, potassium hydroxide, because this is ionic, what's going to happen when it goes in solution is it's going to break apart into your K plus and your OH minus or aqueous. So, although we added copper hydroxide, the only interesting bit, the only stuff which does anything is the hydroxide. The potassium just goes off and has a party somewhere. This is the thing which is doing stuff. So we're going to add some hydroxide. Now, what is this going to react to give? Well, we know we're going to get a copper hydroxide precipitate, a blue precipitate. So copper hydroxide, if we remember from my previous set of stuff on here, had that formula there. All I then need to do is go and balance my equation. So if I've got 2 hydroxides there, I must have started with 2 there. And let's not forget, I've essentially swapped these hydroxides for the waters. So I must have plus 6 H2O. So as long as you learn the formulas of all the different complexes you need to know about, it should be obvious what's going to happen from your equation. If we're reacting hexaqua copper with hydroxide, we're going to get a copper hydroxide plus the water left over. We'll just try one more. Again, we'll start with we'll do a cobalt one this time. 2 plus. And let's say this time we're reacting with hydrochloric acid. So again, HCl, that's going to, a strong acid, is going to break apart into H plus and Cl minus. So let's add my Cl minus. And what's going to happen is we're going to get another ligand substitution. And well, what do we know which is a complex which has cobalt and chloride in? Well, it was CoCl4 2 minus. So all we need to go back is go back and balance that. And we'll need 4 chlorides there, because there's 4 on that side. Let's not forget my 6H2O. Okay. Probably the most difficult one you're going to have to do is that one with copper bonded to both ammonia and water. And the way we do that is by adding ammonia. So we start off with my hexaqua copper. And what we're going to do is add a little bit of ammonia. So we'll start by adding like a dilute or a small amount of ammonia. Ammonia is an alkali. Weirdly enough, it can react with water to release OH minus. It works like this. Here's my ammonia. It reacts with the water and it essentially rips off a H plus to make ammonium. So I've got NH4 plus and OH minus. So if I was to add a small amount of ammonia, your hexaqua copper wouldn't actually react with ammonia, it would react with your OH minus, in that kind of like the equation we just did. So I would get OH minus, well, copper, OH minus, that's going to make copper hydroxide, a blue precipitate. Let's not forget to balance it. So that would be my first equation. If I was to add a lot of ammonia, it goes straight past this and we get a different reaction happening. So if you add a small amount, a dilute amount, or a concentrated concentrated batch of ammonia depends on the reaction which happens. This is dilute. If I was to add concentrated, then you've got so much ammonia that not all of it can react with the water. So there's some left over to react with your hexa-aqua-copper, and you would basically get that complicated molecule. So 4 of your waters swap for ammonias. We still have 2 waters attached. And then let's go balance that. I've got 4 NH3s there. I must have 4 NH3s there. I've lost 4 of my waters, because look, there's only 2 left. So I must have 4 H2O. Notice how impossible it would be to do this if you didn't learn the formulas of all of these different complexes. Like I say, there's what, 11 or 12 or something stupid like that? Not a lot at all. Providing you know the formulas, you can figure out what it's going to make. I've got copper, I've got ammonia. Well, that's the only one with copper and ammonia in, so it must be that one. Okay? And that is colours in complexes and also ligand substitution reactions. Just a little extra thing as well. If your substitution reaction produces a precipitate, we would call it a precipitation reaction and not a ligand substitution.